Hello everyone. Today we'll be taking the simple harmonic motion lab and the specific simple harmonic motion that we will be discussing in this lab work is pendulum bob, the simple pendulum. So before I go through everything that we'll be needing to do in the experiment, let me show us what a pendulum bob look like. So from the virtual lab apparatus that we'll be using, you can see this is how a pendulum bob looks like. So a pendulum bob is such item that it has a mass hanging through a thread, and then there is a fixed point. As you can see, this thread is fixed to a particular point, and this is the mass that is hanging on this thread. So when you displace objects like this, you obviously know what will happen. And what will happen is that it begins to move to and fro, to and fro, to and fro. And this to and fro movement is regarded as one complete oscillation. So as it's starting from this first blue line, it goes there, it comes back. That's an oscillation. So if it goes again, 1, 2, that's another oscillation. So we need to get familiar with how we do all these things. Well, all these things, we shall be discussing them in this lab as we go ahead. So I will restart this now to suit what we did before in my stopwatch file. So we can go back and check what we'll be doing in this lab now. So the lab says the aim of this lab is to determine the acceleration due to gravity, and the apparatus we will be using, they are the retort stand, clamp and bus, spewed cork, thread, pendulum bob, stopwatch or clock, and a meter rule. Now, based on the virtual lab that we are using, all these instruments, their usefulness, everything has been embedded all together in the virtual lab apparatus that we'll be using. So I can say that our apparatus for this virtual lab is just the simulation page. So because everything we need has been made available there. Now, the objective of this lab is that by the end of this lab, students should be able to construct the composite table. What do I mean by a composite table? Let's quickly check that. So this is what I mean by a composite table. When taking a lab reading, when you're taking a lab measurement, you need a composite table. The composite table will help you record all the data that you might have gathered during the process of the lab. So that's what the composite table is for. And second objective is that a student must be able to plot a graph of L on the vertical axis, that is the length of the thread that is holding the mass in the single pendulum. As it is varying, student must be able to record this value and then plot graph of L on the vertical axis and against the square of the period. The capital letter T signifies the period on the horizontal axis starting from the origin. And finally, student must be able to determine the slope of the graph. So the aim of this experiment is to determine the acceleration due to gravity, which shall be extensively talked about in the theory session. But in this particular lab, we will be focusing on these three parts only. We will determine this, we will construct the composite table, plot the graph, and determine the slope of the graph. So the element needed to determine the acceleration due to gravity will be found in the slope of the graph, which will now be used in turn to determine the acceleration due to gravity in a theoretical session. So without waste of time, I already showed us a preview of how our simulation would work. So we can then go straight to work now. So the first procedure is that we should suspend the single pendulum from the support provided so that the length L of the pendulum equal 100 centimeters. So the simulation is making use of meter. So I will know that 100 centimeters is equivalent to 1 meter. So I'll go to my simulation now. So we can see here, this is where we can vary the length. So the length we can vary from 0.1 meter to 1 meter. So I will leave it at 1 meter as the simulation requires, as the procedure requires. That's 100 centimeters. So having it at 100 centimeters, so the second procedure says that displace the bob of the pendulum through a small angle and determine the time t for 20 complete oscillations. So I will displace the bob. Now, you know what happened according to what I did the other time. the bulb begin to swing to and fro. So all I just need to do is get a perfect reading, that is, get a perfect movement from this first blue line to the second blue line and coming back again, which I will be counting as 1. When it repeats itself, I will count it as 2. Now, I need to time this for 20 counts. That is, I need to record a movement from this place to this place and back. That will be 1. I'll count again 20. Then this is my stopwatch. Once I'm ready to take the reading, once the thread reaches this first blue line here, I need to click on my stopwatch to start counting. So I myself personally, I will be counting that oscillation just like I've instructed us earlier, just like I've showed us how to do it earlier. Then by the time I'm done counting 20, I will come and pause my, let me show you what I'm talking about now. So when this gets to the blue line, we'll have, okay, 1, 2, 3. Now, I've taken the time for 3 complete oscillations now. So we can see what we are going to be doing. So this time, we're doing it for 20 complete oscillations as required by the lab procedure. So I will restart the stopwatch now so that we can start taking the reading proper. So we can go now. Let's wait till we get to that first blue line again. So I start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So on the 20th reading, 20th oscillation, I have 40.17. I can, so that is 40.17 seconds. So I will record this in my composite table. That's 40.17 for the time, but I need to get the period. How do we get the period? The period is the total time taken divided by the number of oscillations. That will be 40.17 divided by 20. You can press that on your calculator as well, as I am doing mine. So this is approximately 2.01 seconds. 2.01 seconds. Not only that, I will need to find the square of that 2.01 squared. So, and that is 4.04, approximately 4.04 seconds squared. So I'm done with the first stage. So let me go to a new length now. The new length I'll be using is 80 centimeters, which is equivalent to 0.8 meters. So I'll come here and shorten the length by 0.2. So we have 0.8. I need to restart the stopwatch, then wait again until they get to the blue line and do the same thing over again. So let's wait. Let's start now. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So we have 35.93 this time around. 35.93. So 35.93 seconds. So the same process again, we will divide this by 2, 35.93 divided by 20, sorry. So that will give us approximately 1.80, approximately 1.80 to decimal places. So 1.80 raised to power 2 now, that would give 3.24. 3.24. That's approximately 3.24 seconds squared. So to the next stage, which is for 60 centimeter, that is 0.6. That is 0.6. So we go back to our simulation. So we have this to be 0.6. Okay, good. So we do the same thing again. Start this, wait for it to get that blue line, first one. So let's start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So we can see that it's getting a little bit faster. The more we shorten the length, the lesser the length gets, the lesser the period that we're getting. So from our knowledge of physics, we would see that that shows a sort of direct relationship, with direct proportionality with length and time. That is, the if we increase the length, we see that the period also increases. If we decrease the length, we see that the period also decreases. So, but these are things that we'll discuss extensively in the theory section. So the time gotten here is 31.22. So let's record that. We got 31.22. That's to period 31.22 divided by 20. And that's 1.56. 56. Then the square of that, 1.56 raised to power 2, that is 2.43. 2.4. Okay, the next one now is when we have 40 centimeters, which is 0.4 meters. 0.4 meters. So I'll be shortening that by 0.2 again. So we'll start the stopwatch and start counting from that blue line. Let's wait to get there. Let's wait. So let's start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So we have 25.48. 25.48. 5.48. So this would be 25.48 divided by 20, which is going to give us the period. That's approximately 1.27. 2 decimal places, 1.27 then raised to power 2 now is approximately 1.61. 2 decimal places as well. So the last data we need to collect is for that of 20 centimeters. That of 20 centimeters, that's 0.2 meter. That's 0.2. So we start the stopwatch and let's start counting once we are ready. Let's wait. So taking this side stopwatch when I was not ready. Let's wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that's what we stop. So we have 17.96. 17. That's divided by 2, 17.96 divided by 20. 0.90. 0.90. When I square that, 0.90 squared, that will give me 0.81. So now that I've constructed my composite table, let's see what I'm supposed to do next. What I'm supposed to do next is plot a graph of L on the vertical axis against T squared on the horizontal axis. So we can say that L on the vertical axis on the Y axis and T squared will be on the X axis, and I'll be starting from the origin. So as I am doing a virtual lab, I'll be using a virtual device as well for the plotting of the lab and of the graph that I want to do. So I'll be using Excel. Excel is one of the most commonly used devices in plotting of graphs, especially when it comes to experiments like this. So all I need to do is get my Excel ready. As you can see, this is my graph book. Nothing is there now. And this is where I will be putting the information which I have gotten. Then automatically it plots the graph for me. I just need to put some settings to make sure it starts from the origin as the objective required us. So let me go and copy what I need on the x-axis. Let me copy that first from our composite table. So for the x-axis, I need this. I need the square of the period. So copying that to Excel and paste it in this column. So as you can see, everything on the x-axis has been changed to suit this scale. So you can see that for every 5 centimeters, there is 0.5 units, that is the half unit. So for 2 centimeters, that is from this place to this place, there is what? There is 1 unit. So the scale for this x-axis is 2 centimeters to 1 unit. So let's see what Excel will do for the length as well. So I'll copy it there. I'll choose this column and put this here. You can see automatically Excel plots the graph for me, and you can see the scale that's chosen. So it's choosing. We have from 0 to 20, 20 to 40. So every 5 centimeters represents what? Represents 20 units. So let's proceed. And so if you really want to do this in a physical graph book, you need to plot this point, trace them out by yourself. Find a place where you have 0.81, which is somewhere around here, and trace it to 20. Find a place where you have 1.61, which is somewhere around here, trace it. So until you get to the last stage. And after you have done this, then you'll be looking for a way to connect this graph as close as possible, such that it meets as many points as possible. So, but Excel has a way of doing it for us. Like I said, I'm using Excel, but this thing can be done. It's just like we do it on our normal graph book as well. So, but since it is a virtual lab, I'll be using these to plot. So I will add a linear. I will look for a line that will capture everything. At the same time, I will make it. So as you can see, this line captures everything already. But going by what was asked in the question, you can see that we need to set the line to start from the origin. So if I set the line to start from the origin, as you can see now, I've edited it on Excel using 0.0. Now there's an easy way for me to get the slope of this graph using Excel. That is by displaying the equation of the chart. And by displaying this equation from the concept of linear equation, the coefficient of x here is my slope, which is 24.73. But if we would be determining our slope using our physical graph book, we know how to do that. We pick 2 points. It can be here and it can be here. So if we pick these 2 points, we need to trace it down. Let me show us a bit what we are going to be doing. So let's say I want to pick 2 points now. If I want to pick 2 points on this graph, let me use this. So I can pick this. So I will narrow down this so that it will be like a point. Yes. So it's really giving me what I want now. So I'll choose that. Sorry, I'm trying to show us what we do if this were to be our normal graph book. So let me take it to the graph. So I'll make it so small. I'll make it so small. That's the point. So I can select it. So I can select it or choose another circle again and make the point somewhere around here. So now with these 2 points, all I need to do is what? All I need to trace is to trace it down. All I need to do is to trace it down with a straight line. So I will note what that is. I need another straight line again to trace it from the point. I will trace it to the vertical axis. Trace it to the vertical axis, straight line. Don't forget, this is just a demo because Excel already got my slope for me. I'm just illustrating how we get our slope. So from this point as well, I'll do that. Go here. Then I'll go for the vertical as well. I'll go for the vertical as well. Yeah. So that is it. So I need to trace this point. I need to get this point. What is it? That will be my x2. And then I need to get this point. That will be my y2. And for this point, this will be my x1 and this will be my y1. So by the time I subtract y1 from y2 and I divide it with, let's see what, let us make an approximate value here. So if this is between 80 and 100 and it is 20, we can say that it is, so it is 5 boxes that is representing 20 units. So if we have 20 units being represented by 5 boxes, that means that each of the boxes will be represented by 4 units because 20 divided by 5 is 4. So this point that I've chosen is a little bit closer. So I can say it is approximately 96, or roughly, let's say 97. So that's my y1, that's 97 minus, let me see, what will my y2 look like? That's approximately 36 or 37 as well. Let me also choose 37. So 97 minus 37, which is my y2 minus y1, that's 60. So let me take care of that first. Then for this place, so that it's almost fall in the middle of 1 and 1.5. So what will be in the middle of 1 and 1.5? That should be approximately 1.25. And for this place, we have this place, 3.5 and 4. So we can have approximately 3.75 here. Don't forget what I'm doing. I'm just doing the rough calculation here. Excel already got what I need for me. So I will have 3.75 minus 1.25, and that is 2.5. So I'll be dividing 60, which was the result I got from my y2 minus y1, which is 2.5. So 60 divided by 2.5, that give me 24, exactly 24. So as you can see, with this rough slope determination, it also correlates with what Excel got because this is approximately 25 centimeter per second squared. 25 centimeter per second squared. So in the theory session, so whether we're still going to be using centimeter, whether we're going to be using second squared, that will be discussed with us. But we have determined the slope here. And what exactly is this slope? Is it exactly the acceleration due to gravity? Or we still have other things to do before we'll be able to determine the acceleration due to gravity from it? So in the theory session, it shall be discussed better. So as we have determined, we have been able to complete the objective of this lab, which is construct composite table, plotting the graph, and determining the slope of the graph. This is the end of this lab, simple harmonic motion, specifically simple pendulum.